So imagine that we take now a vertical axis of revolution, and we take an infinitesimal rectangle that is also vertical and slightly away from the axis of revolution. Now, of course, since the rectangle is vertical, its width is a small change along the x-axis, so it is given by dx. And now imagine that we are revolving this infinitesimal vertical rectangle about the axis of revolution. It will create essentially a little cylindrical shell. And a very thin one, as of course the thickness of this cylindrical shell is the width of the rectangle. So let's inscribe in of our shell our small vertical rectangle. Of course, the center of our shell, and again, this is usually known as a cylindrical shell, or in short, simply shell. The center, of course, of the shell is the axis of revolution. Well, we already have the thickness of our shell given by dx, and as before, we are interested in finding the volume of this little solid. But this one's a little bit more interesting. The question is, how do we figure this out? Well, the idea is simple but interesting. Imagine that you cut through one side of the shell and then flatten it out. You can see that what you have is now a surprisingly simpler solid, a little rectangular prism. And now finding the volume of this shape, of course, is a lot easier, but the volume of this is the volume of the shell. Again, all this is the result of cutting through one side of the shell and then flattening out our cylindrical shell. And you can, of course, reconstruct the shell from the rectangular prism if you simply wrap it around. So, now the volume, as I've just said, is now a lot more simple. We need the thickness of our prism, which is of course the thickness of the shell, which is of course the width of the rectangle, simply dx. We need the height of the prism, but the height of the prism, of course, is nothing but the height of the shell, which is of course simply the height of the rectangle. And we need the length of our rectangular prism, but again, if you wrap it around, the length of the rectangle is the circumference of the shell, which is 2 pi r. So we need, therefore, the radius of the shell. And if you look, the radius of the shell is the distance from the center of the shell to the rectangle. But the center of the shell, of course, is the axis of revolution. So this is the radius of the shell. And again, since we have an infinitesimal rectangle, or width that shrinks to 0, think of the rectangle as a very thin piece of string. And it will make figuring out the radius a little simpler. So now we're essentially done. With the radius of the shell, the circumference is 2 pi r, but the circumference, of course, is the length of the rectangular prism. And so we have the volume of our little shell. the area of the rectangular prism, so the length times the height, so 2 pi rh. This, of course, is the area of the face of our prism, times, of course, its thickness, dx. And this is how you can find the volume of a little shell generated by revolving a rectangle that is parallel to an axis of revolution. And of course we can reproduce the exact same result if the axis now is no longer vertical but horizontal. So let me quickly reproduce the exact same argument. The only difference, of course, is now the width of our rectangle is a small change along the y-axis. So it is given by dy and not dx. And before the shell was standing up, now it will be, of course, on its side. We have the height of the shell being the height of the rectangle, the radius of the shell being the distance between the axis of revolution and the rectangle, and the thickness of our shell being, of course, the width of the rectangle, dy. And just as before, the volume is given by 2 pi rh times, of course, the thickness, which is now dy. And that's it.